Welcome to Equinox, where Rob and I are striking the balance between the light and the dark. This is episode 21. My name is Joseph Darnell, and I'm joined by my good friend, Dr. Robert Carter. Hello, Rob.
Hello, Joe.
In this episode, we're going to continue our discussion with atoms because we didn't finish the outline for last week.
Not even close.
Yeah, but before we get to that, how are you doing?
I'm doing fantastic. How are you doing?
I'm really fatigued. I get allergies around this time of year, and I've been treating them. I felt like a wreck yesterday when we originally wanted to record, but okay, I'm doing pretty good now.
What's blooming at this time of year?
I don't know. Whatever the bees are, pollinating. The grass is growing outside. I see a lot of leaves and foliage out there.
That's interesting. There's one thing that gets me in the spring. It's just in my eyes. My eyes feel like sandpaper.
Yeah.
And I don't know what that is, but one year it got me 3 times. It got me in Atlanta and it went away. And a couple weeks later, I drove up to like northern North Carolina and it got me again. And a week or two later, I went up to Indiana and it got me again. I was like, what is this? And I never bothered to check the pollen records to see what was there.
Interesting.
So you could do that. You could see, pollen records, what's blooming right now. And you could say, oh, that's what gets me, if you're interested.
I could. I mean, I've talked to my doctor and they told me how to treat it. They've pointed out that, it was something. And I was like, okay, about 5 years ago. And I've already forgotten what it was. As long as I know what to take.
I know a lot of people in South Florida are allergic to mangoes. And so when the mango trees bloom, they got their eyes just swell up and they have this really bad allergic reaction to mango pollen.
Yuck.
Yeah.
Okay. I know somebody else at the office, I think it was at the office, or maybe this was my aunt, who told me that when in Georgia, from March on, she just automatically takes her allergy pills like every day. It just assumes that she's going to get a really bad case of it. So she goes ahead and just takes the pills.
Yeah, it makes sense.
I wait to get my symptoms. I don't feel like taking the treatment until I got the disease.
Yeah, I try not to take any medicines unless absolutely necessary. And allergy medicine is not something I want. But then again, I don't have them real bad. And if you have them, I'm sure those people, that it's like life or death sort of stuff.
Yeah.
Function or not function. So all of you allergy sufferers, I can only vaguely sympathize or empathize with you, but I do understand it's a struggle.
Usually I get it now and then I get it again at the end of the fall.
Interesting.
Sometimes November is really rough.
Interesting. It's pretty specific. I wonder what that is.
Now, you're down in Florida right now, aren't you? Aren't you on vacation?
Yes, I am. And it's amazing because we can use the internet to do a long distance audio recording, which is really cool. But I am. I'm in the Naples area.
Naples.
Taking my kids to the beach twice now. What we do is we show up at the state park at 8 o'clock in the morning, and there's no one on the beach. We've had the beach 2 mornings in a row, all to ourselves.
Very nice.
We don't have to worry about social distancing because there's nobody there. And about 10 o'clock-ish, when the sun starts coming up, that's when we leave. Because I'm very light-skinned. My children are very light-skinned. Sunburn is no fun. And we get the best water and the most free beaches, and the sun is just lovely, and the water is warm, and we've been really enjoying this. We built a massive sandcastle this morning.
Very nice. I have not been on vacation this year. My wife right now is visiting family out in Oregon. She's having a great time, but we miss each other.
Oh, I bet.
I have the whole place to myself. It's been different this week with getting the allergies and also being home alone.
Oh, terrible.
I was a little bit nervous about the sound of my voice, but I think I sound pretty good. Do I sound about normal?
You sound normal to me.
Good.
But then again, I'm hard of hearing, so
Okay. Now, why is that? Have you ever explained your hearing on the show?
I've never talked about hearing on the show, no. When I was in my 20s, I was having all this trouble hearing. And so I went to the audiologist and he says, you're hyperacusis. It's like, what? He goes, you have above average hearing at all frequencies in both ears. And so, in other words, I couldn't filter out background noise.
Oh.
And probably part of the reason why I've been an introvert for much of my life is because in crowds, I can't listen. I can't hear people talk. It's just rah, 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 all the time. And then several years ago, maybe 4 or 5, I was having a lot of trouble speaking for CMI at churches in certain situations. And I was having a lot of trouble in the foyer after an event when I was trying to run credit cards and talk to people and stuff. And I was really like, I am audio challenged. And so I went and had my hearing tested again, which is cool because I had a baseline from when I was 23 years old. So now I'm 45 or 46 and I do it again. And sure enough, the high frequencies had dropped off a lot. And in my left ear, it had dropped off even more.
Oh.
And so I got hearing aids and I love them. They're awesome. Plus, I have Bluetooth.
Nice.
I got Bluetooth in my head. I could literally be staring at someone and listening to music and they would never know it.
I had no idea.
And right now is a treat because I'm over at my sister's house and my brother-in-law has a company in Naples where he installs a high-end audio and personal movie theaters to, rich people's houses in Naples. And so I'm sitting in their movie studio that they have in their house. And this is one of the most deadest audio environments I've ever been in my life.
Incredible.
Almost, except for one. When I was a kid in a computer club in high school, we took a trip to a company that was doing the first generation, what's that called? Please deposit 50 cents in the machine to continue your call. You know those old voices where all the words are pre-recorded and they throw all the words together to make a sentence and it was never right?
Yeah, the call systems.
Yeah, that company was doing it. And what they had was they had a sound booth that was cut off from the factory. So you went through two doors and the doors didn't touch. And it was a room within a room, but the inner room was sitting on a column of concrete that was like 50 feet tall in a hole in the ground. And so it was like 50 feet of concrete straight down and it wasn't touching. It was like on a pillar and it wasn't touching the dirt until you went down 50 feet.
Oh, wow.
So a couple episodes ago, we talked about maybe even last time, talked about walking into the Watts Bar cooling tower and the unbelievable echo in that tower. Well, in this case, walking into this place at this company, the sound was so unbelievably dead. It's hard to explain it. Because you as an audio person, you know what dead sound is like. And it's just different. And it's not natural. And this was the most absolutely unnatural thing I'd ever been in. It's like my ears are like, I don't hear anything. It was just strange. And so here I am in a movie studio with lots of sound deadening tiles, and it's almost that good, but not quite.
Very nice. I love my audio equipment. I've not had the occasion to use such an audio booth, but I have visited radio stations where a friend of mine used to work. They are really interesting.
Yeah, they're really cool.
I get a little claustrophobic in the smaller ones, and I need some ventilation. I'm kind of spoiled at home that my sound equipment is good enough. I don't need those kind of booths. I kind of feel like it's a little bit overkill for some of the professionals. I don't really need it 80% of the time. But I do appreciate that carpet is a lifesaver. A lot of houses without the carpet, then you would just think that the problem is the entire room. But it's not really the entire room's fault. It's often just that the floor needs wall-to-wall carpet.
Take care. A lot of the problem, yeah.
Yeah, it takes care of a whole lot of the problem. And then the last 10, 20% of the problem could just be having a good isolating microphone.
Yeah.
I'm in good shape right now.
Well, I don't know if the audience knows this, but when we're recording and I'm at home, most of the time I'll take all my couch cushions and build a little couch cushion fort, and I'll stick my head in there, and that's where I do my recording. Now, a couple of times I've just sat at my desk in my living room, and I can tell it's more echoey.
Huh.
So if you're getting into podcasting, well, Joe, didn't you tell me that a lot of guys, if they're traveling, they'll sit on their bed and pull the blanket over the top of their head?
Yes. A lot of professional radio and podcasters, what they'll do is they'll have to do interviews, and they may have to do those back to the radio station from a hotel room where they've just gathered information for a report. They grab the blanket and throw it over their head to record and send it back to the station. It's awesome.
Brilliant.
Yeah.
Yeah, I have a hard time now listening to tinny triangular waveform audio broadcasts, podcasts, because there's just, it's not like I'm super picky, but it's just hard to listen to now because I can tell the difference between someone who just did a little sound muffling and someone who's sitting in a bright environment and it's all like this and it's just very difficult on the ears.
Yeah, be careful with that. For me, it's a pain enough to hear when I apply certain filter effects improperly when I'm manipulating audio, accidentally making the S sounds even harsher than they already are.
Ouch. Yes, yes.
So be careful with your own equipment. Whew, your poor ears. let's go ahead and get into the continuing discussion of atoms.
All right. I'm worried.
What's the worry about? You know the stuff forwards and backwards. You already explained to us what an atom was in so many intricate details last time. This is your territory. You're in your moment.
Yes. And I love this stuff and I eat it up. But the question is, can I explain it to someone in a way that makes sense? And that's what I've been wrestling with. Well, when we get into the middle of the atom, we're going to talk about quarks and colors and flavors and strange and charm, and everyone's eyes glaze over. They have no idea what they're talking about. So what I've tried to do is distill it down to the absolute bare bones. And if you know this, then everything else is built on that. And that to me makes sense.
Okay.
So as long as I know, what is the absolute most fundamental of the fundamental of the fundamental, we start at that point and build from there. And that's when we add all these very complicated words that you only hear once or twice in your entire life. Then maybe things make sense.
All right. Well, then what do you want to pick up?
Well, let's start with an atom.
An atom. Hi, Adam.
Hey, Adam. How you doing, man? So anyway, you remember the atom from high school, right?
Yeah.
Okay. What's inside an atom?
Well,
the basic parts of an atom.
I remember the nucleus from last week.
Okay. And the nucleus has two things in it. Protons and neutrons.
Neutrons. Yeah.
And then outside the nucleus is an electron or electrons.
Yeah, I remember the electrons and the neutrons. I forgot the protons.
Well, protons are really important. In fact, they're more important probably than anything else because you can strip away the electrons and you don't change the type of atom. It's still the same element. You can change the number of neutrons and it's still the same element. But if you change the protons, you have different elements. So uranium, lead, gold, hydrogen, that's the number of protons.
Okay.
Take away the electron out of hydrogen and you have an ion, but it's still hydrogen. Add an extra neutron, you have deuterium or tritium, but it's still hydrogen.
Interesting.
So the most important thing that defines what an element is the number of protons.
The number of protons.
Number of protons. We call that the atomic number. So hydrogen, 1 proton, atomic number 1. Helium, 2 protons, atomic number 2. And up it goes.
I'm with you so far.
Okay.
So how did they determine those numbers? Was it the first one was discovered became number 1 and the second one discovered became number 2?
Wow, that's interesting. No, we already knew about 50 or so elements before we arranged them in order. In fact, we need to do another one on the periodic table. Maybe not next week because we've already done atoms and atoms. Before that, we did energy. Maybe we need to give our listeners a break. Maybe not. The periodic table of the elements is unbelievably cool and how that all worked out. But we already had 50 or so elements and they arranged them and they realized that hydrogen is really, 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 really simple. It's a proton and electron. And you can have a couple of neutrons in there, maybe, which gives you an isotope, another big word, of the same element, hydrogen. Fun stuff, huh?
Now, you just referred to isotopes. Can you explain isotope real quick?
Okay. If the basic definition of an element is the number of protons, and if you have a certain number of protons to have a balanced atom, you have the same number of electrons. So if you have 20 protons and 20 electrons, the total charge is 0. They balance each other out. Strip away a couple of electrons, now you have an ion, but it's still the same number of protons. But a lot of elements can have extra neutrons in there. A neutron can be there or not be there. It's necessary to stabilize some of the larger atoms, but like hydrogen, the number of neutrons is variable because it doesn't have a charge. It's not important for, stabilizing or binding necessarily. It's there or not there. It's just a neutral particle.
Okay.
And atomic number is the number of protons. The atomic mass, how heavy that thing is the number of protons plus the number of neutrons. The atomic mass of hydrogen is not 1. It's 1.00784 because there are some hydrogens that have not just a proton, but have a neutron. Some have 2 neutrons. Some have extra neutrons, and they're very rare. A pure, perfect hydrogen would have no neutrons. It would just have atomic number 1 and atomic mass 1. But if you took like all the hydrogen in the room that you're in right now, and you purified it, and you weighed it, it would weigh a little bit more than hydrogen with no neutrons because every once in a while there's a hydrogen with an extra neutron or two. Those are isotopes.
Isotopes.
Isotopes are very important for things like atomic bombs because the two different main uranium isotopes, one of them's really good for bombs and one of them's a bomb poison.
Okay. Well, how do you poison a bomb?
Well, because it absorbs neutrons.
Oh. Okay.
One of them is really, really good for atomic reactors that generate electricity, and one of them is really bad. And so one of the big things they had to do, like we talked about Oak Ridge National Labs last time, one of the big things they had to do is they had to separate the uranium isotopes. And what they did is they made a tunnel like 5 miles long, and they put uranium hexafluoride, which is a gas, 6 fluorines in a uranium atom, which is toxic and radioactive.
Oh.
And they put it in this tunnel, and they let it diffuse down this really long tunnel. And of course, the lighter isotope, the one with fewer neutrons, moved faster. So they're able to separate the uranium isotopes based on their mass because one of them traveled faster than the other. And so when it finally got to the end of the tunnel, the first stuff to get there was the lighter uranium. They'd pull that out first, and as the heavy uranium got there, they'd stop. And then they'd empty out the tunnel again. They'd pump all the air out, and they'd do it again and again and again. And they enriched the uranium that way to get their uranium-235, which they needed.
Okay. So is the uranium-235 like the stable stuff versus the unstable stuff?
Oh, no. No. They're both radioactive, but they have different half-lives.
Half-lives. Okay.
And they release or absorb neutrons at different ways. I don't want to use the big words. I'm trying not to use big words here.
Yeah.
But they're just different.
Sure.
And if you want a chain reaction to happen, you want one of those and not the other. And that's how they did that first enrichment of uranium. Now, the plutonium came from Ernst Lawrence's laboratory in California, which we also talked about last time. So we had the uranium for the first bomb and the plutonium for the second bomb using two different methods, but both of them were dealing with the mass of the different isotopes and how do you separate isotopes? Because chemically they're the same. They have the same number of electrons. So they react the same to all these different chemicals. But once you react them, like uranium hexafluoride, it's a gas, and the heavier ones go slower than the lighter ones. In the same way, if you were you go to one of the ice cores in Greenland. And you go down the ice core, you could measure oxygen isotopes and oxygen isotope ratios. And you can tell things like the temperature of the water that the snow came from when it evaporated.
Oh, wow.
You can tell how far away the edge of the ice shelf was. Because when water evaporates, the lighter oxygen, H2O, the oxygen has different isotopes, but the heavier isotope oxygen doesn't evaporate as fast. But then once it's in ice crystal form, the heavier ones fall out faster. So the further away from the edge of the ice sheet you are, the more your snow has traveled, the lighter the elements are because the heavier isotopes have already fallen out to maybe 1/1,000,000%. But that 1,000,000% is measurable using high-tech instruments.
Okay.
So isotope chemistry is really important.
Huh.
And the difference is protons versus neutrons.
Okay.
We okay with that so far? You think the audience understands what we're talking about so far?
I understand it.
Okay.
I don't necessarily understand the full practical application.
Okay, fair enough.
When I think about atoms, I remember that this is stuff that has furthered invention, technology, and the sciences for the last 100 years.
Oh, yeah.
Power supplies, as we were discussing last time. I didn't realize how much the atoms depended upon energy and the relationship to energy until you explained that last time. It's really interesting stuff. What I wonder is is it essentially true that it's sort of like when we were talking about molecules a few episodes ago, that once you reach a certain scale, you just cannot really appreciate what it really means. When it's so small, you cannot understand fully the ramifications of something being infinitesimally small.
Yes.
And it's like that with these minute details of the atom particles. But the difference is that unlike, say, the distance between one molecule and another, when we're talking about atoms, there's hundreds, if not thousands, of practical ways that science is able to take advantage of this information.
Yes.
And in ways that are far more concrete and more readily practical in real research.
And it's that practical that's the most interesting part of this, because the low-hanging fruit's already been picked. We've already figured out all the stuff in science. The next set of scientific advances are going to be based on some of this ultra nerdy stuff that we've been talking about. It's going to be, the ability to take two subatomic particles and mirror them and link them together so that when you disturb one of them, the other one instantly disturbs, and it doesn't matter how far away it is or where it is.
Oh, that is neat.
So you get faster than light communication. We've already experimented with this. The Chinese have already done it. They've bound two particles, one on Earth and one on a satellite, and they disturbed the first one, and the second one instantly disturbed, and they clocked it, and it's at least, 20 times or maybe 20 orders of magnitude faster than the speed of light.
Oh,
in other words,
that is amazing.
It's as fast as they could possibly measure. If they had a better instrument, they might be able to measure it as even faster.
Oh, that is so cool.
Quantum entanglement is the future of cryptography, because you can't intercept the signal. And if you disturb one end of it, the other end it gets disturbed too. It's like, hey, someone's sneaking up on our signal here. You'll instantly know it. And this is the future of cryptography and the future of communication. So if we send a satellite, past Pluto, there won't be an hours-long delay in communication. It'll be instant. Or if we go to Mars, it's no 8-minute delay in light travel time. It's instant communication.
Huh. Wow.
So all of these things that we're talking about are critically important. They are going to rule our world. And the people who understand these things will be the kings of the future world. And yet most of us, myself included, hated high school chemistry so bad we never learned it.
Oh, man.
I despised my high school chemistry class. I took 3 years of college chemistry at Georgia Tech.
Uh-huh.
Okay, I got straight A's in organic. No one else did, but I loved organic chemistry. The other chemistries I did not do so well in. And my first job out of college was teaching high school chemistry. And that's when I learned it. When I had to explain these things to 10th graders, and they didn't get it and didn't get it and didn't get it. And finally, how about that? Oh, that makes sense. Oh, cool. So I learned all these new ways of explaining it. But even though I had a technical education, I still didn't understand these things. And so if we can get a grasp on this, even if we're not the leaders, we'll at least understand what's going on. It's really important to know what's going on in the world. In the world of science, for me, it's really important. So that's why I think part of the reason why we started this podcast.
Yeah. Yeah.
All right. So,
okay, I have a question for you.
Yeah. Well, yeah, please ask.
What is the relationship of atoms to conditions like solids, vapors, gases, liquids? Is there anything interesting that happens on the level of atoms?
Absolutely, in all those cases.
Yeah.
But all the things you mentioned are made up of atoms. The thing that's not necessarily made up of atoms is a plasma.
Oh.
Which is just a ball of energy or a streak of energy. A whole bunch of atoms that have been ionized and they just kind of streak along in energy. But that's a whole nother discussion for a whole nother day, probably.
So when something is frozen on the atom scale, how is that different? Any unique properties that are like how does it go from just being really motionless to being really cold? How does it go from being really cold to being part of a solid?
Again, whole sorts of other avenues of exploration. We can cool down atoms to pretty close to absolute zero. You're never going to get there, but we've gotten to within, a very, very close absolute zero, and they pretty much stop moving. That's not the same thing as being in a solid, though. The atoms in a solid are often moving. They're wiggling, they're straining, the energy flowing through that solid is making them wiggle. They just can't wiggle out of the solid or it breaks down. But it can get hot. So a bar of iron that's hot, those atoms in there, they're vibrating, they're wiggling back and forth. They can't necessarily get out of there because they're bound to all the other atoms, maybe covalent bonds or something like that, but they're definitely vibrating, wiggling, moving. They're just not flowing in a solid.
Okay.
So in one sense, they're not moving, but in the other sense, they're hot. Cold, get it down to absolute zero or close to it, they're cold and they're not moving.
So then on the other end of the spectrum, when the atom gets really hot, it's moving all the time really fast?
Absolutely, yes.
Okay.
You can see that mainly in like boiling water. The energy is flowing through that water. And because hot water is less dense than cold water, the flame at the bottom of your boiling water thing is heating those molecules up and they rise. And the cooler ones at the top fall. And so you get water flows in a boiling water, a pot of boiling water. All right, but we haven't actually gotten to the nature of our conversation yet.
Okay. Then let's tackle it.
Okay. So we understand now atoms. And atoms are made of protons and neutrons in the nucleus, and outside of that are electrons. We got that the atomic number is the number of protons, and that dictates to you what element it is. And there's a variable number of neutrons, and that gives us isotopes. And the atomic mass is a number of protons and a number of neutrons inside the nucleus. And so you can have the same element with different atomic masses, like tritium and deuterium. Right?
Right.
Now, okay. Now this is where it gets really, 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 really strange when you ask, what is a proton or neutron made of?
Oh, okay.
And this is where it gets so esoteric and so weird. And for some reason, the physicists had a field day and making funny names for things.
Oh. Huh.
And it is not helpful. Like, if I told you the fundamental particles, the smallest thing, the thing that everything else is based on, are called quarks. Your reaction to that is
what?
Exactly.
Yeah.
At the base, as far as we know, at the base of matter are things called quarks. There's a guy in my hometown. I don't know why his son wasn't super brainiac, but this guy drove this car and it had a bumper sticker. It said, "Beware of quantum ducks. Quark, quark." Now, today, I wish I had that bumper sticker, but 99% of the world would have no idea what it means.
Right.
Now I'm like, this is a great bumper sticker. But anyway, it was back in the 80s. So we have quarks. And the issue is there's so many different types of quarks. And they have such weird names. And they talk about colors and flavors. Flavors? What?
What? Yeah, really? Do they mean flavor or do they mean something else by that term?
It's just a type.
Oh, okay. Classification.
Like all the different flavors of people.
Okay.
That's not the right one. It's not really, you would never say that. I'm trying to think of, because we use the word flavor as type.
Yeah.
Not just taste. And that's what they mean. Colors also, it's just type. And they talk about spin. And some of these things, it's as if they had spin, but they have no size, therefore they can't spin. Huh? But they talk about spin anyway. And those things are really esoteric. So I said, okay, let's cut to the chase. I knew that some of these things can transform into other things. And at the very base of everything, the base of all matter, are three things that are really just little packets of energy. They're fundamental. They don't break down. They don't change. One of them is the electron. The two others are quarks. The up quark and the down quark.
Oh, okay. So how do you spell the word quark?
Q-U-A-R-K.
Okay, that's what I thought.
And if we just get that and just stop there, and we don't talk about fermions, and we don't talk about bosons, and we don't talk about hadrons, these are all different combinations of these things. But if we just understand the most basic level, there's the electron, the up quark, and the down quark, and everything else is based on those things, life might be good. depending on how you combine these quarks, gives you different levels of complexity.
Okay.
They call them generations. First generation is the up quark, down quark, and electron. Second generation is different combinations of those things. Then there's a third generation. But those things will break down over time into up quarks, down quarks, or electrons. So they talk about the standard model of the atom, which is brilliant. It took them hundreds of years to work this out. And it's really probably finalized in the 60s and 70s. And then with the discovery of the in the Large Hadron Collider, the God particle, the Higgs boson.
Ah, yeah.
With the discovery of the Higgs boson at the Large Hadron Super Collider in Europe, they completed the standard model of elementary particles. There are 6 quarks. There are 6 things called leptons, one of them being the electron, but then the muons and neutrinos, or 3 types of neutrinos, and a tau particle. Those are like, what? But most people get electron because we learned about that in high school.
Yeah.
And then the quarks, we can't observe them. We don't actually know that they exist.
Really?
But because we've never seen them by themselves. They have to exist to explain everything, but we've never seen it except for one of them, the top quark.
So the up quark.
Now, not the up quark, the top quark.
Oh, big difference.
It's a third generation quark. No, it's a combination of combinations. It's so big, it actually has a mass larger than the first 75 elements.
Oh, huh.
So this is weird because it's a big old honkin' particle, but it's a particle. It's not an atom.
Okay, so I'm with you so far. When you say particle, it's technically smaller than the atom.
You think so, except the top quark is massive.
So like we were saying last time.
But it also breaks down. It falls apart.
Huh.
It's not stable. And yet it's in an atom smasher, you can see it. Oh, there it is right there, because it curves this way in this magnetic field, and it curves at this radius, therefore it has this sort of a mass. The other ones, though, we've actually never observed. They instantly recombine in different ways.
Yeah, of that. Wow.
Cool, huh? Maybe. But strange. All right. If you look at protons and neutrons, a proton has 2 up quarks and 1 down quark. But the quarks have a charge. And this is just the weirdest thing in the world.
So in addition to the electrons, the quarks has an electron-like charge?
Yeah, oh, exactly. It's measured in electrons. Negative 1/3 is a down quark. So negative 1 is an electron. Negative 1/3 is a down quark. Positive 2/3 is an up quark. This is surreal. Why on earth? Well, if you add, a proton has 3 quarks in it, 2 up quarks and 1 down quark. That gives you 2/3 plus 2/3, which is 4/3. And then a negative 1/3. So 4/3 minus 1/3 is 3/3, or positive 1. So a proton has a positive 1 charge.
Huh.
Yeah, huh? What? But we know it's true only because all the experiments ever done back this up. It's just like we know gravity's true, because every time you drop an object, it falls to the earth.
It always goes down. Yeah.
And it always falls at the same rate, the same acceleration, because of the mass of the earth. I mean, gravity works in every single case ever done, ever, period. It's like in our gravity episode we did several episodes ago, it is the biggest engine of scientific prediction mankind has ever discovered. Gravity theory. That's why it's the law of gravity. Well, when we're talking about subatomic particles, we're not talking about laws, we're talking about a model. But all the experimenting is telling us that an up quark has a positive 2/3 charge and a down quark has a negative 1/3 charge. And when you put 2 ups and 1 down together, you get a proton, which is a charge of positive 1. But a neutron has 2 down quarks with charges of negative 1/3 each, and 1 up quark with a charge of positive 2/3. So positive 2/3 minus 1/3 minus 1/3 is 0.
Okay.
So
how does that math work? 2/3 plus
minus 1/3 plus minus 1/3 is negative 2/3.
Okay.
Plus 2/3 is zero.
Okay, yeah, then
zero.
we're back to zero.
So the proton and neutron have the same mass, but they have totally different charges. One is a positive 1 and one is 0. And then the electron, of course, has a negative 1 charge. Now, I cannot even begin to tell you why quarks have 2/3 or negative 1/3 charges. I'm not sure that anyone actually knows. I don't know if there's a reason for this. It just is. And once it
Yes.
is, it's just this fundamental thing that is true in the universe.
Of course.
And even though the human mind rebels at this because we want to know why, but you know what? When we get to the ultimate subatomic particles, there's not going to be a why. It just is, because you can't go any further. There's nothing. It just is.
Right.
Now, we could be wrong. Maybe quarks are made up of strings, superstring theory, or maybe there's particles, and maybe we make an atom smasher that's as big as a solar system, and we get these things going so fast we smash quarks together and they break apart to other particles that we've never seen before. Maybe true. But as far as we know, with what we're able to know now, we have these fundamental particles called quarks. They have a spin, they have a charge. You add them together in different ways, you get protons and neutrons, or other higher level things that aren't stable. But protons and neutrons are incredibly stable. They stay together. But you do need some other particles, because you know that like charges repel. That's one of the things we learn in high school science. A positive plus a positive, they're going to repel each other. Just like the two north ends of a magnet, they repel each other.
Right.
Well, it's true for charges also. Now, negative and positive, they stick to each other, or they annihilate each other if they can touch. But the reason the electrons are bound to an atom is because there's a positive charge in the nucleus. And the reason the atoms, if they lose an electron, they'll steal an electron back again because they want to be neutral. And want is a bad word. They don't want anything. They don't have a brain, but they will automatically drive toward neutrality, because if you lose an electron, it'll suck another one in to balance the positive charge. If you gain an electron, it'll throw it away because it'll be repelled. But wait a second. If positive charges repel each other, how can you have so many positive charges inside the nucleus?
Oh, huh.
The nucleus should explode.
Basically push itself apart.
It not just push itself apart, it should explode with prejudice, with an unbelievable amount of energy, with an earth-destroying amount of energy.
Well, Rob, do you know the answer?
Well, there are other subatomic particles.
Other subatomics.
One of them is called the gluon.
Wait, now isn't this the one that I heard about a few years ago that scientists just made up and they don't actually know what it is?
No.
Oh, okay.
Well, okay, this is pushing the limits of my knowledge here. I'm not sure if we've observed gluons or not. Interesting question. That's beyond my limits of understanding at the moment. But they do have a mass, and they have to be accounted for. So if you break an atom apart, hey, wait a minute, there's extra mass we lost? Oh, we'll call that the gluon. And what the gluon does, it orchestrates what's called the strong force. So they're fundamental particles and they're fundamental forces. We haven't quite figured out how to get all of this to be explained in one sitting. I mean, the smartest people in the world have not figured this out yet. But we have these fundamental particles and we have fundamental forces. We have the strong force, which holds the protons in the nucleus using gluons.
Well, okay.
There's also the weak force, which also operates inside the nucleus. There's also electromagnetism, and then there's gravity. And of those four, gravity's the weakest.
Given all the particles and the atoms that that like dust can just float around in the air. So an atom doesn't necessarily get affected by gravity per se, and all atoms fall.
Not even remotely. I mean, gravity might as well not operate at all inside the nucleus. The strong force, the weak force, electromagnetism, they're so much stronger than gravity at that scale that you can ignore gravity entirely when you're doing your calculations. Gravity doesn't apply to a molecule. It doesn't apply to a cell. It applies to the Earth, the moon, the sun. Gravity rules the universe. but it is the weakest of the 4 fundamental forces. Though I have heard that they recently determined that there's a 5th fundamental force. Yeah, it's called duct tape. Sorry, that was a joke. You're supposed to laugh.
Well, I was about to say, is gluons another property of Elmer's?
That'd be funny. That would be a good comeback. That's an old Georgia Tech joke. Strong force, weak force, electromagnetism, gravity, and duct tape. Ah ha ha! And everyone laughs because a bunch of geeks in a room, they do stuff like that. Anyway, so we got fundamental forces, fundamental particles. Put that all together, and we have this idea called the standard theory. We could be wrong. Everything we've done so far is pointing in the direction of this is correct. And one of the disappointments with the Higgs boson was that it was exactly correct. They're like, oh man, we don't have anything new to learn. There's no exotic stuff. We don't, it didn't open up any new areas of exploration. It said, yep, we were right. What a dud. What a tremendous letdown.
I don't think so, because it is actually nice to get to the bottom of some things. Like the universe itself is so big, and then there is the quantum realm. I mean, the quantum realm is a real realm, right? Like, or whatever we want to call that.
Oh, yeah.
So it is nice to get to the bottom of some things and know, okay, that territory has been explored. Here's the bottom of it. There's the very last neutron. Now let's go find something else. I don't know, like, do you not appreciate that? Like, as someone who, like, I to my understanding, there's a few mathematical problems that have never been answered and they haven't figured out the answer. So theoretically, we may never figure out the answers.
No, I'm a little disappointed. I'm a little bummed, actually.
Yeah?
Yeah.
Okay. What would you like to see happen?
Well, let me give an example in biology, right? Since I am a biologist, I'm not a particle physicist, but in biology, we just keep learning more and more and more and more, and life just gets more and more and more complex. And genetics is insane, and the molecular machines in the cell are insane, and it's just, there's no end. We're not approaching the end of biological complexity, but we have reached the end of subatomic complexity. So boring. That's my reaction. Even though there's still a lot to learn, it's just different. Now, maybe we can blow quarks up, but not using any energy level that we're able to perform here on Earth. This is God level physics, not human level physics. This is literally beyond what science can conceive of physics, which is kind of disappointing because it means that the bar is set so high that we can't even, why even bother to reach that bar? We can't do it. That kind of stuff.
So is it true that if you have a shrink ray, you can just decrease the space between the atoms and make people small?
Oh, yeah, of course.
Yeah. Okay. I thought those Disney movies were scientifically accurate.
Oh, my. Oh, my. No. All right. So let's reel back here again. Let's go back to the 10,000 foot view.
10,000 feet.
10,000 foot view.
Hello up there.
As you are not an uber nerd. You're a regular person, and yet you're extremely intelligent because you're sitting here with this conversations, asking me all these questions, all these episodes. I mean, this is a lot of fun.
Sure.
But from a non-scientist, what's the next question you would ask?
Oh, about the atoms?
Yeah. Should I care?
Well, something along that line.
All right.
I would also be curious about, are there more relevant kinds of atoms for some intriguing scientific reason that I am unaware of?
Well, interestingly, quite possibly, because we've reached the end of the periodic table. When I was in high school, we hadn't finished it yet, but now we have. We've got all the periodic tables up through the rows that we have. Well, can we now, because you go from hydrogen to helium, and then loops back again to lithium, and that runs to neon, then it loops back again to sodium, and it loops and loops and loops. You have all these rows. Well, we've gotten to lawrencium. Now we've gotten to OG, whatever that is. I forget. Element number 118. Is there an element 119, which would be, again, on the left of the periodic table? Can we add another row? Now, of course, people are wondering about this, but probably not, because probably that element will be so unstable it can't hold together. So anyway.
Okay, well then going back to the other question, or the other suggestion, what did you say a second ago? Yeah, something to the effect of, then what does it all mean?
Yeah, what does it all mean? Should we even care about all this crazy stuff?
No, we totally should. Undoubtedly. But it takes somebody with a scientific inventor's practical mind to understand what he needs to do with this now that he can take advantage of it.
Well, yeah. Every little thing we do, we learn something, and not only can we take advantage of it, but like I said earlier, it's going to drive the world in the future. There's some discovery to be made where all of a sudden we're going to get a lot better battery storage, or a lot faster electrons in a wire, or a lot more complicated computers, or better air conditioning, or a cell phone that never needs to be recharged.
Oh, wow, that'd be incredible.
Those sort of things are there for us, but we got to figure out things that are really hard to understand. And it's sad in one sense because it means that most people get bored of it. But in another sense, in the adage, in the kingdom of the blind, the one-eyed man is king.
Yeah.
Well, that's like this stuff.
Oh.
If we can even begin to understand a little bit of this, we will have an advantage over most other people.
Interesting.
Yeah.
Fascinating. Well, I think that's going to wrap it up for this week. You agree?
I think my brain is full.
Good.
And we skirted around a lot of difficult issues.
Oh, yeah. Super tough stuff. Thank you. You did a really good job.
Well, thanks. And we didn't use a lot of big words, which I was trying to avoid the big words, which has made this hard.
I think you passed your test.
I think everyone now is going to have a pretty good introduction to the complexities of the atom.
Excellent. Honestly, this has been great for me as well, because I remember some of these details and others I do not remember hearing in high school. So thank you very much.
You're very welcome.
And thanks to every one of you listening to our show and joining us on this quest. If you want to dig deeper into these topics, you can find links to everything that Rob was explaining in the show notes on our website. So go over to nightowl.fm/equinox/21 to get to those links. Or if you're right there at the podcast player, the show notes are also with this episode in whatever your podcast app may be. You should also check out Rob's content at biblicalgenetics.com. His Facebook page and his YouTube channel are by the same name, where you can see the videos and join the discussions of the comments. Follow along, like his page on Facebook. If you want to catch up with me, I'm at JCS Darnell on Twitter. Until next time, goodbye, Rob.
Goodbye, Joe.
And you have been listening to Equinox.